All right. Good morning, everybody. Welcome to week 4 of Advanced Hydronics. My name is Jim DePalma. With me today is Johnny Resso, who will be running questions, but he's also going to finish week 3, so you're going to see him in a minute or two. In the background, in the hot seat, is Chris, and Eric's working our cameras. So we're really looking forward to today because this has been a lot of fun for us. Please be sure all of the handouts that we have given you, you have at your fingertips, because we're going to get into troubleshooting today. All right. And you're going to need all that information in front of you so you can figure out pipe sizes, GPM, and pick circulators. If you're going to get the most out of today, you really need your handouts in front of you. Don't forget, on your screen, you can manipulate how you see what you're looking at. You can click on the the 3 hashes between the camera and what you're seeing in the, from the PowerPoint, and expand and contract the screen to your viewing pleasure, how you want to see it. All right. So without any further ado, John's going to come up. He's going to finish your homework assignments with you from week 3. Okay. And then we'll continue on with week 4.
Okay. Good morning, everybody. So we left off last week, and we kind of left you with a couple of problems, as if you were moved into a service manager type role. You have a technician in the field, he's calling you and giving you all this information. So it's an 80,000 BTU boiler. The indirect has the ability to absorb 80,000 BTU. It's a cast iron system with priority hot water. So we'll do that through the TACO relay. We got zones, 4 zones. They're 2 gallon per minute each. The boiler itself, cast iron boilers, just in general, will have between 2 and 3 feet of head loss normally between a cast iron boiler sections. The indirect has a coil inside of it, and we're giving that a head drop of 6. The whole system, the longest loop, gives us a 6-foot head drop. So we want to go through, we want to look at, normally we would go through, if we're in the classroom together, you know, we would size the circulator, we would size the system pump, and a bunch of different things there. We would do the manifold sizing, and we'll do a little bit of that today. Zone sizes and such. So what we did here this morning is we just drew this out. So this would be our cast iron boiler, right? So it's 80,000 BTU, which we said in the spec. So I have an 80,000 BTU boiler. The indirect in here is a coil. Okay, that coil has the ability to absorb 80,000 BTU. And these are all hypothetical numbers, so don't go out there and hunt for the indirect that only absorbs 80,000, because majority of them will be higher than that. Okay, and then we gave you, we came up off the boiler with the header. We go to a system circulator, and then we also have a circulator for the indirect. And then we have 1, 2, 3, 4 heat circuits, and we have zone valves on the back side. The way this is piped, we would have to run both circulators to make hot water. Okay, so let me just do this, and I'm going to add over here. So if you did it that way, and then I'll remove the circulator from here. If you drew it either way, it's acceptable. So we wanted to show you both ways this morning. Just, you know, now if I do a heat demand, I only need to run 1 circulator. If I have a hot water demand, I can prioritize hot water and only run 1 circulator. So, you know, we're really splitting hairs here with electric efficiency, but if we're going to install a system and try to get the best performance out of it, we might as well take advantage of what our system controlling will do, and Jim's going to dive into that in today's class. So that's what it would look like if you look to your, whether you go to your TACO book, or I know we sent out the pipe sizes with the delta T's. If we were looking at this, I got 80,000 BTU. You can start firing answers off to Jim. I'd like to know what size my supply header and return header would be to handle the 80,000 BTU. You could also fire off to Jim what size our system heat circuits. Each heat circuit, what size would that have to be? And you can fire it off to Jim what size our piping to our domestic hot water, the indirect, would have to be. So pipe diameter for the indirect, pipe diameter for the header and return, and pipe diameter for my 4 heat circuits. So the heat circuits up here, we know they're 2 GPM, so this is 2 gallons per minute. There's 2 different answers we'll accept there. The most common, I think you'll nail. The other one, you can look at it and figure it out. And then here, it's going to be another pipe size. Jim, are you starting to get some answers in?
One answer, Keith came in for the supply,
Okay.
1 inch.
Okay, so Keith says we need a 1-inch supply, and I concur. So that means we will need at least a 1-inch return to carry the BTU out of the boiler and back into the boiler. What size are we going to send over to our indirect? 80,000 BTU. We'll stick with the theme here, 1 inch, right? And 1 inch back from our indirect. So now we can take every BTU that this boiler produces, size the circulator correctly. We have the pipe size correctly. We'll be able to drive that indirect to full capacity. So 1, 2, 3, 4 heat circuits. We have a circulator here that would be sized to handle the full gallons of flow and overcome the highest head, which the system head is 6 feet of head. So 6 feet of head, 6 feet of head, 2 gallons each, 2, 4, 6, 8 gallons, 6 feet of head at 8 gallons per minute. That's what we would use to size that system circulator. Over here, we need to overcome 6 feet of head for the indirect. The boiler is 2 feet of head or 3 feet of head because it's cast iron. So we're going to have to overcome 6 feet of head, and we want to move 8 GPM to get full capacity here. That's what you would use to size this circulator. Heat circuit piping size, anybody send you what size that should be?
1/2 inch or 3/4. I came in from Peter.
Beautiful.
3/4 from Richard.
Most common you're going to see out there is 3/4, but if you look at your chart, and we do this on purpose to make you guys think outside the box a little bit, it could be 1/2 inch, but we know in all reality, more than likely, that's going to be 3/4. And then we will utilize the TACO switching relay to give us priority hot water. Okay, so that's what that would look like if your tech was in the field on the phone, talking to you at your desk. He gives you all that information. You would be able to draw that out, and then you could help him troubleshoot. You know, if there were, the circulators were not sized correctly and we didn't have enough flow, or it wasn't sized correctly, you couldn't overcome the 6 feet of head. So that's what that drawing would look like. So hopefully you came up with a drawing that's pretty close to that. And do I have the clicker? I have the clicker. Here we go. Want to go ahead 1. Oh, the drawings are not in this one. Okay. I lost my screen. Oh. Okay. So that's what it would look like for a cast iron type system. And then we also asked for a condensing type system. So here we have, this would be a condensing boiler. Okay. And in our scenario, this boiler, this is 100,000 BTU. The indirect has the ability, the coil in this indirect has the ability to absorb 150,000 BTU. That's pretty common. Your 40, 45 gallon indirects, that's where it'll be in that range for the most part. We have 4 zones. Each zone up here is 2.4 gallons per minute of flow. And we have a circulator there, so you have 3 circulators involved here. This circulator is going to take care of your 4 heating circuits. This circulator will take care of the boiler's flow across the heat exchanger. And when we're in priority hot water, this circulator will flow across the indirect, come back, and also have the ability to overcome the head restriction of the boiler. So this is what it would look like. We could be using the boiler control to prioritize the hot water and drive the circulator. We could be using TACO relay panel. Depends on how you want to do it. Majority of the time, we would use the boiler control to handle this circulator, which is the boiler circulator, and we would use the boiler control to handle this circulator, which would control domestic hot water priority. And we would go through the same scenario here. We got a 100,000 BTU boiler. What size pipe would we have leaving the boiler? Based on your pipe charts, you can throw Jim some answers. Our headers, what do we need up here for pipe? But the real question I want to ask you guys is, I have a 100,000 BTU boiler. What am I doing here with this circulator when I have 150,000 BTU worth of absorption here in the indirect? Am I sizing this for 20-degree delta T? Remember, Universal Hydronic Formula, page 44, that TACO book, 20-degree delta T, Jim gave you the shortcut, take the comma, move it over one slot. So this boiler needs 10 gallons per minute, right? If I look at my indirect, Universal Hydronic Formula, 20-degree delta T of 20, take the comma, move it over. This needs 15 gallons per minute. So when I size this circulator, do I size it for the 15 GPM or do I size it for the 10 GPM? In this scenario, really all I have is 100,000 BTU to move. So I can size it for 15 GPM. It's going to, take my delta T and shrink it a little bit probably because I'm moving more water than I need to. But reality is, if it puts me up to a higher volume circulator that costs more money, I really only have 100,000 BTU to drive to this indirect. So this was probably sized the way it was based on volume that the house needs. And I always stress in these classes, it's less money to buy storage than it is to buy BTU. I don't want to oversize a condensing modulating piece of equipment just because it modulates. And I'm going to give you the reasons why here, okay? If I take one heat circuit, 2.4 gallons per minute, right here, 2.4 gallons per minute. Universal Hydronic Formula, 20-degree delta T, right? 20 times 500 equals 10,000, okay? 10,000. 2.4 times 10,000 equals 2. Correct? Okay. Yeah, the whole peanut gallery is laughing right now, that's okay. It's early. All right. So if I take the comma now and I move it back, I'll be 2.4. Multiplying it by 10, I take the comma, I move it over, 24,000 BTU. 24,000 BTU. The reason I'm bringing this up is that's my smallest demand. So if I were to upsize this boiler to get to that 150, I need to know the turn down rate. What's the bottom of that boiler's capability? So if it's 100,000 BTU, I may only be able to turn down, who knows, if it's a 3-to-1, whatever, but I want to get somewhere down in that 25,000 BTU range with that boiler because this is my smallest load. If I go ahead and put in a 300,000 BTU boiler that I can only turn down to 60,000 BTU, I now have a system that's going to work like an on-off boiler. And I take the modulation factor out of it because my smallest load is 24. I can't get down there with a 60,000 BTU at my minimum input rate. So this is why we like the right size condensing modulating boilers. We want them to modulate within their range, 10 to 1, 5 to 1, whatever it is. Our NTI boilers that we offer, we got 10 to 1 turn down rates on them. So we can get down to these lower numbers, but I would not oversize my boiler. I would right size my boiler to handle the load. And usually in our footprint, a lot of times we're sizing for hot water. Just make sure your boiler can turn down to the minimum load within the space, or we're going to create short cycling. We're going to have parts fail prematurely because of that. We're going to elevate the maintenance and operational cost of that piece of equipment. And we really want this boiler to live a full, comfortable life and supply the homeowner with the most comfort that we can. So that wraps up week 3. If there's any questions there, Jim?
No,
We're good to go.
Everybody's good to go.
Some guys fire in some pipe size answers, and we're set with that. And all right, it's Jim's show now.
All right, everybody. Yep, it's a great class. It's a lot of fun. I wanted John to finish week 3 with you since he had brought you to that point. I want to make sure that everybody's using the materials that we've given you, so you're going to be able to follow along today. So we're just firing up week 4. Just give us a moment here. All right, here we go. Week 4 is up. Everybody should see that. Okay, so we're going to review. Oh, I need the mouse there, Chris. Okay, here we go. So here's our agenda for week 4. We're going to review everything we've done from week 1, 2, and 3. We're going to go over our switching relays, because as we're building these systems, we can build some pretty sophisticated systems. We want to make sure that we can control them. And we have a great actual setup on switching relays. Will allow you to do that up to 120 zones for a lot of jobs. Very sophisticated systems you could do, and it's quite simple. And then we're going to get into, excuse me, I'm so excited. We're going to get into our favorite part of the class, root cause troubleshooting, where we're going to give you problems. We're going to give you problems, and you guys are going to have to figure it out based on all the information that we've given you since day 1. All right. So here goes our review. So to make sure everybody's on the same page, universal hydronics formulas you see on the screen, we use it every day to figure out our GPM. GPM equals BTUH divided by delta T times 500. And as John just showed you, as we can figure out GPM by using this formula, we can also reverse it to take a GPM and turn that into a BTU. So I'm going to give you a clue. That's going to be one of the things you're going to need to do when we get to the troubleshooting section, the root cause troubleshooting section. Any questions on understanding this formula? Because we use it every single day. This is how we're sizing our pipes. This is how we're sizing our circulators. I've gotten a lot of requests over the past week and a half on sizing circulators for guys that are troubleshooting some radiant jobs that weren't working well. And this is the information that we use in order to do that. So any questions on this, John? Anybody?
So far, so good.
All right, let's continue on. So here, if you want to take a screenshot of this, what we did for you is we did some different scenarios for you, same BTU, but we went from a 10 to a 20 to a 25 to a 30-degree delta, and you can see how the GPM changes. Now, this is something to really pay attention to, because depending on your project, you may want to open up the delta in order to downsize some piping. You have the ability to do that, and you can also use that to save some cost on the job. We'll do this a lot, especially when we're doing snow melt systems, where sometimes the supply and return piping to a remote manifold could get kind of pricey. So if we open up that delta, go to a 25, go to a 30, you can see on 100,000 BTU, from a 20-degree delta, it's 10. If I go to a 30-degree delta, it brings it down to 6.6. That's a pipe size change, and that could be substantial on the project. All right. So take a picture. All right. Save this, or just do the math yourself. But you can plug in whatever delta you want, do the math, and come up with your GPM. All right. Baseboard at a 20-degree delta. All right. So we're showing you the max amount of footage. These are very good numbers to always keep in the back of your mind, especially on 3/4. Here where we're showing you 67 feet. Don't go past that, all right? If we just go past that, we're just gonna have less output at the end of that loop. All right, so if you're troubleshooting a job and you have a loop that has an excessive amount of baseboard on there, now you know why, and you're probably going to want to cut that loop down into 2. All right, now again, as we're going along here, you can take a screenshot of anything here and save it so you have that for the future. Next, BTU capacity for copper and iron pipe. So you can see here, we give you the average flow rates, 2, 4, 8, and so forth. That's to stay within the 4 feet per second. And we'll also show you on this chart the capacity based on the different delta T's, 20, 30, and 40. You'll also notice on this chart, as we open up the delta, make it larger, we can also bring up the capacity of the BTUs that pipe is carrying, okay? So if you're gonna get involved in stuff like this, do your math, make sure you can, you're doing it properly, and always reach out to us if you're not sure. All right. Pipe sizing, again, this is in your take-o handout. These are the GPMs for 3/4 through 1.5 inches, as you can see here, to make sure we stay within that 2 to 4 feet per second, so we don't cause noise, we don't cause any erosion. All right. Everybody should remember when we were talking about air, John talked about getting air out, right? We definitely want to make sure we're not any slower than 2 feet per second. Otherwise, bubbles get big, fat, and happy, belligerent, and they could cause a problem. All right. PEX pipe sizing. This is in your take-o handout also. We're seeing a lot of jobs where guys will do their near boiler piping all in hard pipe, which is great. And then they start feeding their zones in PEX pipe using 3/4 PEX. Inside diameter is smaller than copper. Flow rate will be different. It's plastic pipe. We want to make sure we're not over pumping, because we can erode that pipe quicker than we can metal pipe. So use these charts that you see here for sizing your pipe size based on your GPM when you're using PEX pipe. Okay. Next, flow. All right, velocity, is that important? Yes, it is. I kind of alluded to this already. We want to make sure that we're always staying within that 2 to 4 feet per second. If we go above 4 feet per second, I haven't had enough coffee this morning, I apologize. If we go above 4 feet per second and get into that 8 foot per second range, we're going to cause noise, we're going to cause erosion to our system. All right. I'll give you a quick example. I was talking to a gentleman yesterday. He knew that he was going to have a problem on a radiant job that he inherited. And he said, the 007 is going to be too small head-wise. What should I use? I did the calculations, and he ended up needing a 009 for a very small bathroom. And he was using 5/16 in mud and feeding the manifold for that bathroom with 1/2 inch. Everything he inherited, he told me. Using a 009 in that instance would work, but really don't want to do that. So he's going to re-engineer the job. We're going to see maybe we could do that as floor warming. We got a question.
So we got a question, gentleman asked, you referenced PEX piping. He asked about crimp style and expansion style. Are there differences?
Yes, there is. We're the Uponor rep, so I'm going to be referring to Uponor with the expansion side. And all of our literature will say that we've got a 30% greater flow rate with our fitting on the expansion style versus crimp. What we show people is if I have a piece of 1/2 inch pipe and a 1/2 inch crimp fitting, that fitting has to fit into the pipe, and then the crimp band goes around it. Okay, so that fitting has to be smaller than the pipe. When we use our expansion fittings, Uponor does the ring that goes over the pipe, and then the fitting itself is bigger than the inside of the pipe. So we have to expand it with our tool and then put that fitting in. So it is a bigger fitting. It is a 30% flow rate. So there is a big advantage there. And also one other thing to think about, if I do a crimp fitting versus an expansion fitting, there's really only one way to do it, and there's a perfect visual to show you that it's done correctly. The shoulder of the fitting to the shoulder of the ring would be right against each other. On the crimp side, now I'm not bashing crimp at all, but I'm just telling you, there's too many chances of that crimp ring being either in the middle, toward the front of the fitting, toward the back. It's kind of random. And when we see that on jobs, it's never uniform. So if I was running my company and I wanted to have uniform fittings, the expansion fitting does offer that safety factor, if you want to think of it that way, a good visual to make sure everybody's doing everything properly. All right. All right, moving on, because we got a lot to do today. Indirect hot water recovery time. This is really cool. Take a screenshot of this. This is a big deal for you when you have problem jobs where people are saying, I don't have enough hot water. This isn't working for me. So it says RT is recovery time equals domestic gallons times domestic delta T times 500 divided by BTUH. Okay, whoa, what does all this mean? Well, we're going to give you a 40-gallon indirect, which is the most common. 36 is the available gallons that are available because we've got a coil in that tank. So it's really 36 gallons. We're using 115 as our outgoing temperature. You could change that to 120 if you choose, but we're using 115 as this example. Where does 50 come from? Average water temperature of the incoming water coming into that tank. And you do the math within that parenthesis first. There you get the 65 times 500, because that's the weight of 1 gallon of water, bringing it up 1 degree over 60 minutes. And then we're dividing it by the BTU input of the boiler. And in this example, it's 100,000. So if you plug all the numbers in, 36 times 65 times 500, and then dividing it by that input of 100,000, this tank, we can drain all the hot water out of this tank, and it will recover itself in 11.7 minutes. Why is that important for you? Because you need to then talk to your customer about how are they using their hot water. Are they taking the epic shower, which is over 30 minutes? They could be in there for an hour. That's great. Whatever they want to do is fine with us, but we need to know that. All right. So that means, as John just alluded to you a few minutes ago, maybe you need more storage for this particular customer. Okay. All right. Any questions on that, John? Because that's a key one. That helps a lot of guys out in the field. We're good. All right. Rolling along. All right. So here we're showing you a picture of a cast iron boiler system. A couple of different ways to look at this. Can we make this better? Yes, we can, because the mix valves, let me see if I click, there we go. The mix valves there, they're static mix valves. There's 3 of them. It's pretty rare that on a radiant job, if you're doing a typical home, basement, first floor, second floor, that you really are going to need 3 distinct temperatures. It's possible, but probably not. So we could bring this down to 2 temperatures. Taco does make a I valve, which is a outdoor reset mix valve that'll fit within the same footprint as that standard 3-way valve. So now we can add even more efficiency and comfort to this system. And what that will do is, as temperature changes outside, it gets a little milder. Like today, it's going to be in the 50s. We don't give the same temperature regardless when there's a heat coil. We're going to give the temperature based on what's happening outdoors. Something else to be aware of is that the way this is piped, all right, the way it's piped, it's not primary, secondary, because you can see it's a continuous loop and they're bringing the domestic off here on the bottom. But you also see that we have the returns from that mix valve in front of the supply of this mix valve. So the way this gentleman piped it is not bad, but something to think about. You want to make sure you got your highest water temperature first, because we're going to start blending it down even before we come out of the mix. Something to pay attention to when you're laying out systems like this. It is a cast iron boiler, and if it was just a plain Jane cast iron boiler, you do also have the ability to add outdoor reset to that boiler if it's a young boiler and make it even better. Okay. Condensing, combi units, and just straight condensing heat only boilers. We sell them. That is the brand that we represent. We're very proud to do that brand. They need to be piped specifically. They need to be piped in primary, secondary. Okay. You could do moose antlers. We could do all kinds of things, but you're going to need to do them in primary, secondary. Something to think about when we just talked about recovery for hot water, and John was talking about turn down ratios and things of that nature. When you're doing a combi unit, don't oversize it there also. You don't want to make it so big that even when there's a call for space heating, the unit's too big. And you also don't want to make it oversized even on the domestic side, because if we just get one little faucet calling, these boilers can make heat so quickly that we can short cycle those units also, all right, even on the domestic side. So be aware of that. But one of the reasons that we're talking about condensing boilers was we want to make sure that they condensate. And that means, what is the return water temperature we want to see? 130 degrees. Okay, so we do our heat losses, we do our math. We could take advantage of more baseboard than necessary if it was a replacement job. If it's a new design the system so even on an average coldest day of the year, the boiler condenses, and that's how Mr. and Mrs. Smith are going to get that 90–95% efficient system. Okay. Be aware of the importance of doing heat loss, because as this chart shows you here, we're not at full capacity all heating season. And this heating season's been a really great example. We didn't start out really cold. It was pretty mild, and then boom, it's been cold. And we've been at our average coldest days for the past couple of weeks at night. And we've been in the high 20s during the day. So, you know, earlier on, we were not at full capacity. We were probably at 60 or 40%. But this is showing you that a majority of the time, we're not at critical mass. We're not at our design. Okay. Always do the heat loss. Be aware, take advantage of it. Best sales tool you have, and it'll help you fix a lot of problems. What we're showing you here is baseboard ratings. Every single baseboard manufacturer gives you a chart, and it'll tell you, based on your input water temperature, it'll tell you how many BTUs you will get per foot. So we want to use this, especially again when we're replacing a standard boiler, and I want to take advantage of maybe if it's over radiated, I can run a lower temperature, still get enough BTUs out based on my heat loss, and then maybe offer that homeowner a condensing system. Okay, so you can look these up. Every manufacturer has them. One of the best tools you have out there is called Google. You can find anything. Okay, primary, secondary piping. Right, John went over this. What's going on between the T's? All right, there'll be times that we're going to have flow between the T's. There'll be times we won't. Sometimes it'll be reversed. Okay, it all depends. But what's really critical is that the T's are nice and close. Right, 4 to 8 pipe diameters, as you can see. I always tell guys, put them right on top of each other. It's not going to hurt anything. Do it right the first time, you'll have no issues. As you're looking at this picture here, we have multiple boiler systems. So this is probably going to be on a commercial job. Maybe we've replaced one large boiler and we have multiple boilers there. And you can see that we have our primary loop here, and we've got our circulator for it. And this is size for all the BTUs, all the GPM on the job. Each boiler down here has got its own little circulator that is just guaranteeing the flow through that boiler. Here are our closely spaced T's, and we've just extended them out because what did we do as we piped in these 3 boilers? We piped them in as a reverse return. This way we get even flow across the boilers. All right, very important, something that you can do out there on a smaller scale, commercial job. That you guys can prefab this and bring it to the job. If you need any assistance with this, let us know. Give us a call. All right. Now I want to get into relays. So that was our speed date on the recap of what we've done so far. Any questions there, John?
Good.
All right. So relays, TACO relays. TACO makes SR relays and ZVC relays. We can control circulators. We can control zone valves and circulators. This gives you guys the abilities to wire up your jobs on your own. I don't need to hire an electrician to do this. This also gives you the ability to get your techs, if you hired a new tech who maybe is not very comfortable with low voltage wiring or wiring up controls, we can get him very comfortable with this. And now that tech who's entry level can be wiring up your system. So you're getting more value out of him when he's out there on the job. And these relay controls also help you go after bigger jobs. We can go out to 120 zones with these relay systems. And we've got houses not far from our office here where we've tapped almost that. All right. So, you know, that could be pretty intimidating if you're not comfortable with wiring, but these relay panels make this quite simple. So I'm going to go into that right now. So what you see here on the screen is an SR panel. This is where we use switching relays, and we're using it for circulators. And we're going to zone with circulators. And I'm going to press the button, and you're going to see the wiring come through. So we're going through everything with incoming power to the panel. You can see we're going through a low water cutoff, the service switch, that's at the top of the stairs, right? The switch in the red box, all right? And if there's any other type of switches, and also the circuit breaker from the panel, that's incoming power. And we're bringing it to the panel, and we're bringing it to the relay that's right on the boiler, okay? So that's one side of power, and then we have to do the neutral side, okay? Now, one thing I want to point out in this diagram here, the low water cutoff, that's 120 volt low water cutoff. TACO makes these. That low water cutoff is going to shut off power to the whole system if we have a problem. All right, easy to wire in. Majority of people are using 120 volt low water cutoffs. So you can see how we're bringing power into this. Now at the top, we can now wire in our thermostats. And this is an older picture. Our current SR panels give you an R, W, and C. So if I need constant power to a digital stat, we can supply that with our panel. So we have anybody's thermostats can work there on the top. We have a priority switch you can see here on the right-hand side. The last zone on these panels is always domestic priority. So if that's what you're going to use it for, you put that into the on position, and now that zone is prioritized. So if there's a call for space heating and domestic at the same time, space heating gets delayed. The priority is domestic hot water. And then once that is satisfied, then we would take care of space heating. What would be next? We would just wire our circulators here on the bottom. Okay, so again, very simple. And then what's after that? We've got our isolated end switch right on the left corner of the panel going to the TT on the boiler. Okay, so behind me here, we're showing you a single zone switching relay. We're also showing the same thing that I just put up on the screen. Okay, and this is our expandable version. So you can see down here, we do show you the A, B, and C for expansion port. So I would set up one of my relay panels as my primary. I would set up my second relay panel as a secondary. I would take A to A, B to B, C to C. I would do that with standard thermostat wire. I would set that to master on the primary. The second one would be the secondary. It says slave. We would set it to slave. Okay. And now all communication between the two boards happens, and my primary or master, that end switch is what's going to turn on the boiler. We also give you another end switch on here. So if it is a condensing boiler and it has a second TT on it for domestic to tell the boiler to high fire, we give you that end switch there too, so you can bring it to the boiler. Makes your wiring simple and easy. Okay. R, W, and C, like I just alluded to, so I can give constant power to our stats. And again, the last zone is our priority zone. Now these panels have lights. So the lights are there not for entertainment. The lights are there to help you troubleshoot. So there's going to be a green power light. And then if any zone calls on the SR panel, that zone light will light up and it'll be red. Now I call those troubleshooting lights because if I get the midnight call and I show up at Mr. and Mrs. Smith's house and they're complaining of no heat, if I see green light there, I've already saved myself a lot of time. I've got power right to my switching relay, and I should have power to my boiler. Like, let's go find out from that point what's going on. I don't have to run back to the panel to see if we've tripped a breaker or anything. And then if I'm getting calls for heat and zones are lighting up, but the zone that they're complaining about, say the master bedroom is cold, it's not working, I don't get my red light, all right, then I know I probably have a bad circulator. Any questions on that, John?
So far, so good.
All right. Moving on, we have the same thing for zone valves, the ZVC panel, 404, 406, and we also have them as expandable, again, out to 120 zones. So you can see by the screen that we have on the PowerPoint, same thing, incoming power coming through our service switch, through our low water cutoff, into the panel. Now, the way this is drawn, the transformers are outside of the panel. All right, and that's the way UL only allows them to be drawn on a diagram, but those transformers are inside the panel. So there's one side of incoming power, and there's the neutral side, so we've completed that circuit, okay? Then again, I can bring any type of stat I want. I got RW and C on top. My last zone would be my priority zone, and I have the priority switch on there. If I flip that to on position, now my last zone is prioritized. On the bottom, I can do 2-wire or 3-terminal or anybody's standard 4-wire zone valves at the bottom. You'll see where we're using a 2-wire that we're putting a jumper across terminal 3 and 4. So what does that mean? On the ZVC panel, the 1 and 2 is your motor. That's the power to the motor. 3 and 4 is the end switch. So if I use a 2-wire zone valve, and that could also be a 2-wire actuator from a radiant manifold, we're putting the jumper across 3 and 4. We're telling the panel that we've closed the end switch, okay? The zone valve where you see 3 wires, that would be my Takeo 571. When we do our wiring class, we show you that valve. It is a 3-terminal, but it actually is a 4-wire. But when you use it with our ZVC panel, it's just terminal 1 to 1, 2 to 2, 3 to 3, and that zone valve is done. Anybody's 4-wire zone valve, all right, so if we're going to go with the standard everybody's comfortable with, the Honeywell, your 2 yellows are your motor. That's going to go into terminal 1 and 2. Your 2 reds are your end switch. They're going to go into 3 and 4. If that was the Takeo Zone Century, oh, it's hidden. I'm going to get it. It's the Takeo Zone Century. I don't know if you can see it here, Chris, if you can zoom in, but we do give you labeling of 24 volts. We do label end switch, and it'd be the same thing. Thermostat wire here would go to 1 and 2. Thermostat wire here at the end switch would go to 3 and 4. Okay. One other thing I want to show you here is we have our isolated end switch going to our boiler. And as you can see right down here, we have the ability to drive 3 pumps. We can drive a system pump if we want to call it that, or the boiler pump. We can drive a domestic hot water pump. We can also drive a secondary or a zone circulator. All right. It depends on how you pipe up your system, whether you've got domestic or not, whether you're going to do direct hot water or not, however you're going to do it. But these contacts here, these are called dry contacts. So they're switches, but we have to bring power into them. So on the power point, you're going to see we're going to bring power into them. All right. Here we go. So power's coming in one side here. All right. Then power is going to come out. We're going to pick up one side of the main pump. All right. We're calling that the system pump. Then you also see that there's a jumper coming across to the common. All right. Think of common like an exit ramp off of the highway. Power can go to either side, right? So if I get off the highway, I can either go right or do the flyover and go to the left. So power can do the same thing. So we're bringing power into common. And now I'm taking power out of normally open to my domestic pump, and I'm bringing power out of normally closed to my secondary pump. That's just bringing power in, and then we completed, this is the white wires, we've completed that circuit. Now what happens if any zone on this system calls? What will happen is this main pump end switch will always close. It's a normally open switch. It's in the open position. So if any zone calls on this panel, it's going to close. So now I would end up powering this circulator. Since I have my secondary pump on normally closed, this will stay closed if any zone calls, except if the priority zone calls. So now I'll end up driving 2 circulators. So this could be my circulator that's on my boiler, if I want to control it here. And this would be the circulator that would be sending out water to the system. Okay. Then if we get a domestic call, what will happen is the pump end switch here will still close. All right, it'll always close, but now my normally closed switch is going to open, and the normally open switch will close, and now I'll power my domestic circulator. So depending on how you pipe up your system, you can decide how you want to sequence your pumps. All right. So great option, very simple, really easy. Again, this one also has the lights on the board. You'll see lights over here on the side, and this is a great diagnostic tool because I got the green light on top to show me that I have power. Then every zone gets 2 lights. There'll be a red light for, I'm sorry, a yellow light for the call, and then that telling you there's a call for heat. That means one of the thermostats closed. And then when the zone valve actually opens, then I get a red light, and that's telling me the end switch made. So a great diagnostic tool there. Everybody that's on this class today, everybody who's been on our 4-week classes can wire this up. Everybody, all right? All you need is to have power brought to this area, but all the low voltage wiring, everybody can do. All right, so don't be afraid of this. Get involved with it. It'll help you grow your business and save money. We've got a question.
Okay, so one of the questions is, why would you utilize the DHW circulator on there instead of using a zone valve on the circulator?
Great question, and we are going to give you a problem going forward. Flow, all right? John just showed you how much a coil can absorb, how much flow I need to get there. Depending on the GPM that you need for that indirect will determine whether you're going to use a zone valve or a circulator, all right? And I don't want to give it all away because we do have a great troubleshooting coming up. But keep that in mind. It's based on flow, how much I need to make that coil, how much flow do I need for that coil to absorb so that indirect can perform. Based on flow, keep that in mind, all right? All right. And last but not least, so since I am going to use a circulator for my domestic in this scenario here, we're showing you that we're putting a jumper across 3 and 4 on the priority zone because we have to tell the panel that the end switch is closed. All right. Any questions on that? Everybody calm, comfortable? All right. Please take advantage of these. It'll really help you grow your business. One other thing I want to show you here is the ability to expand. Like I told you, we can go out to 120 zones. So here we're showing you expanding to switching relays to the SR panels. So the wiring is still the same. Incoming power to both panels is the same. All right. Then the thermostats connect, aquastats all connect the same. All right. Same thing with our circulators. But when we get on our expanded panels, we do give you an extra port for a primary circulator. So if you're zoning with pumps, all right, but you know, closely spaced T's, but you want a circulator for the primary loop, all right, or your system loop, however you want to call it, we do give you an extra contact there just for that system circulator. All right, so again, we have our dip switches to make the primary or master panel and the secondary or slave panel. We have our dip switches on there to make sure the system's got a priority zone if you want. Then we have our expansion port, the ABC, where A goes to A, B goes to B, C goes to C. Now the 2 panels talk to each other. And then my primary or master panel is the panel that's sending the signal to turn on the boiler from the main end switch, and also another end switch to tell this particular boiler, hey, high fire for domestic. We can daisy chain this out to 120 zones. Okay, so now don't be afraid of a big job. I don't need an electrician to do this. We can do this. Okay, and that last pump that we just added there, all right, I'll show you down here. That's that extra terminal for a primary circulator if you need that. Again, it's always going to depend on how you pipe up your jobs. Next one, we're showing you we have the ability to add outdoor reset with a single switching relay. This is called our fuel miser or an SR501 OR. And we're adding it to an existing pump panel. So let's say somebody has an older Takeo panel or somebody else's panel, and you want to add domestic priority and you want to add outdoor reset to the system. You could do that by using this SR501 OR. What we're doing here is we're coming out of the end switch from this panel and we're going to the SR501. Okay, we're going to the TT there. We're running an outdoor sensor to it. All right, We're running a boiler return water sensor because we're giving it outdoor reset. We're taking the end switch out of here to our boiler. We're taking power into it. All right, we're running the circulator there for domestic hot water. And one last thing, what would be for the aquastat on this older panel, we're jumping across to our SR501 OR so we can prioritize that. And what will end up happening if there's a call for domestic, all right, we still shut off space heating and domestic gets the call. All right, yes, sir.
Jim, real good question here. Gentleman asked is, do you have to cycle power when you're hitting your dip switches?
No.
You don't. I told him it's always just best practice to power down, make your dip switch changes, then power back up.
Yeah.
You can do it live, but just across the board with, other products, it's just best practice.
Best practice, always safe to do it that way. I mean, if I know what I'm going to do beforehand, I could set my dip switches. But if it was powered and we made the change to the dip switches, nothing would happen.
And then why are there 2 transformers in there?
Great question, and my bad for not talking about it. What Taco does by having the 2 transformers is we split the panel. So the first transformer, this is a 4-zone, is taking care of the first 2 zones. The second transformer is taking care of the next 2 zones. So I really am not interested. I don't really care what combination of zone valves you use here. I'll have enough VA to support it because we split the panel with 2 transformers. Something to keep in mind, something that's coming up more and more often, you're using Nest thermostats. A lot of you guys will show up on the job and the homeowner says, here, this is what I want you to use. Or the utility gave it to me. I want you to use this on my job. And if you've got everybody else's zone valves down here, that combination of Nest and everybody else's zone valves is too much power. The Nest would actually need its own transformers. But if you use the Taco Zone Sentry, all right, the Taco Zone Sentry is only a 0.06 amp draw. We only pull power to open. We only pull power to close. So since it's a 0.06 amp draw, the lowest amp draw on the market, if you use Zone Sentries here on the bottom and you use Nest Stats on the top, that combination will work on these panels. So something to keep in mind. Great question. Thank you for bringing that up. All right. All right, moving forward, if we've got no other questions, a little bit more of the recap here. Base load cast iron and condensing boilers. This picture here, we're showing you that maybe on this job, we had a couple of large cast iron boilers that were not lead lagged or sequenced in any way other than the first one always came on, and then the next one came on, the next one came on. And over the years, we just beat the crap out of those couple of boilers. And also the building owners were saying that, it's costing them a lot of money to heat the building now. Can we make the system more efficient? What can you do for them? So what we're showing you here is if you prefab your header and do closely spaced tees, I can replace maybe a couple of large cast iron boilers with multiple condensing products. Because remember the one screen we showed you, we're not at full output all heating season. 40% output, 60% output, right? And now I can, if I pipe them in the primary, secondary fashion that you see here, and also in a reverse return fashion, now I can lead lag the boilers. I can set them up however we choose based on that manufacturer's control. We'll get nice flow rate across the boilers. We'll get good runtime across the boilers. And if that last cast iron boiler was still viable, leave it on the job, we probably won't have to fire it majority of the heating season. And let's say this was a school or a municipal building. I was firing a big boiler plant in order to make domestic hot water. If I'm just taking care of sinks, I just could put an indirect on there and prioritize that zone. All right. So something to think about if you're walking into a project like this that maybe you thought wasn't within your wheelhouse, wasn't in your comfort zone. Well, you can still do this because what we're showing you here is really no different than what you would do residentially. Yes, the last boiler, the way it is piped is now become a radiator because just the way it's piped. But you know what? It'll work fine on this job. You know what'll happen? After they see after a season or two how much money they've saved, they're probably going to come back to you and say, hey, let's change that last one out, turn that into a condensing boiler, and then you can really finish it up and make it a nice primary secondary system. Okay, I hope you were really paying attention to that, because there's lots of opportunities out there. Think of municipal buildings, think of churches, think of schools that have these big boilers that maybe they just can't maintain them anymore. So you got a nice opportunity to go in and do something like this. All right, now we're getting into our, no, we're not getting troubleshooting yet. Still doing the review. Sorry about that. All right, so static pressure, we talked about how to make sure we understand the proper PSI we need for our system. We're measuring from the boiler level, the water level of the boiler, top, middle, bottom, depending on the boiler, up to the top of the system. Whatever that distance is, we're going to do what? We're going to multiply it by 0.43, and then we're going to add another additional 4 PSI to that number to make sure even at the top of the system we have at least 4 PSI. So you'll see here on the bottom, here we go. Here's my remote. That even for a standard 2-story house, you do the math, it comes out to 11 PSI. Remember when John was talking about the expansion tanks, a lot of them come charged at 12 PSI. Now you know why. Typical 2-story home, boiler in the basement, you do the math, it comes out to about 11 PSI. The tank is charged at 12. But we're getting into more projects in the inner city where we're now at 3 stories, 4 stories. You got to do your math, know what that PSI needs to be for the system. And what do? What did John tell you? You got to change this. We change it before we install it on the system. Pump it up with your pump, get it to the proper pressure, then install it on the system, and you'll be good to go. Take a screenshot of this if you missed it the last time. Pumping away, we talked about this. All right, what's the job of the circulator? The job of the circulator is to provide a pressure differential. That's how we're going to move the water through the piping, okay? We call them pumps, they're really circulators, so it's creating a pressure differential. What the diagram is showing you on the PowerPoint is we have the circulator on the supply side. We're pumping away from the expansion tank. The expansion tank is the point of no pressure change. So in this scenario here, it's a 2-story home. I got my 12 PSI at my tank. That will never change. So now if I've got my circulator pumping away from it, my circulator will now add positive pressure. So in this example here, we are telling you the circulator is going to add an additional positive pressure of 4 PSI. We're telling you based on elevation, there's an 8 PSI drop when we get to the top of the system. So if I just had gauges on and the system's sitting there doing nothing, I will see 12 PSI on the suction side of the circulator because that cannot change. But on the discharge side, it'll be now an additional 4. There's my 16. Because of elevation, I got to overcome an 8 I lose 8 PSI because of elevation of a resistance. And at the top of my system, I'll have 8 PSI. All right. You can fix a lot of jobs out there just by moving the circulator to pumping away from the tank. Excuse me. Pumping away from the tank, add that positive PSI. That'll help you drive air out of the system. All right. So if you got a job where you're going there every year to bleed the top of that system, you know Mrs. Smith by name, and you know all her kids because you're going there every year. Move the circulator, and you can stop that from happening. Any questions on that, John? Because that's a big one. We really want to make sure people understand.
So far, so good.
So far, so good. Okay.
Oh, hang on.
Back
You
up.
need space between the pump and the tank.
Well, yeah, but there's no
minimum.
no minimums or maximums. No. What's going to be hard for you is where the job is, and if it's a really tight area, if you just have room. Okay. So if I don't have room, let's take advantage of other things that we've talked about. If I don't have room and I can't move it, change that air scoop to a 4900. All right. No piping minimums needed. This will get the air out of your system too, and you can fix that problem. All right. What's next? Distribution piping. We don't care what the boiler came tapped with. All right. They made 1,000 that day. Every single boiler is going to get tapped the same way. So we decide our pipe size based on what, gentlemen? the GPM we have to deliver, how many BTUs, how much GPM. That's what will decide our pipe size, okay? So we're going to use our formula, GPM equals BTUH divided by delta T times 500. All right, so if on this scenario here of a 75,421 BTU job, everybody should know instantly that this is 7.5 GPM. I don't even need to do math. As John showed you, and I've talked about it, move the comma to the left. There's your GPM. So super simple, super easy. That tells me my GPM, 7.5, call it 7.6. Now you know what pipe size you're going to need coming out of that boiler. Oh, Cape tapped at 1.25 inches. You don't need 1.25 inches, 1 inch will do. Any problems if I use 1.25 inches? Not at all. It's easier on the circulator, but just costs you a little bit more money. All right. Same thing for our zones. Once we know our GPM per zones, then we can size our piping accordingly. Okay. Any questions on that? Because we use this every single day and we're beating it to death, but we're doing it on purpose because we want you to be comfortable with this. We're good to go. All right. Okay. Air eliminators. We talked about air eliminators. We talked about the air scoop. We made sure that you know that you need a minimum of how much piping in front of the air scoop? 18 inches. To calm that water down, to get a nice smooth laminar flow for that air scoop to work. Your boiler's underneath the stairs in a tight area and you can't get that 18 inches in. What's the next best scenario? Use the air separators. In the world of TACO, that's our 4900. All right, we're not the first guys out there. There are other ones out there. You've heard of them before. Hey, what's it called? Spiral vent? Yep. But use ours. We've got some very distinct advantages to it. The cone shape at the top is very important because this traps the air. It's not wet. It's not always flooded. We don't get leakers. We truly don't. We get less than 0.5% back out of all the ones that we sell over the course of a year. We don't get leakers. You do have the ability to close the air vent once the system's been running and purged. You can close it, okay? So you don't need to put a metal cap on it or anything like that. There's just a little screw slot there, and you can close it up. We have the pawl rings inside, as you can see here, and as the air bubbles come into the pawl ring, into the chamber, hit the pawl rings break up those air bubbles into tiny micro bubbles. Then we fill up our cavity up here and vent the air out. This will save you time on your install. This will save you time on your purging. I mean, I've got guys telling me it saves them at least 30 to 40 minutes purge time, depending on size of system. All right, time is money. Take advantage of it. ECM series circulators. We've been talking about this now for quite a while. The line keeps expanding. TACO just introduced the 0026E, 0034E. So now we have ECM circulators that can replace all of our 00s. We now, the 26E and 34E can replace the 10s, the 11s, the 12s, the 13s, the 14s, and even get us into light commercial, okay? Take advantage of circulators like this. Why not have the circulator, which is the heartbeat of the system? Why not have that circulator be able to adjust its speed based on zones opening and closing, either by a pressure differential, or if you really want to make it nailed right, by a temperature differential, a delta T. And especially if my boiler is going to be modulating based on outdoor temperature and demand, if my circulator can maintain a specific delta T, it just makes for a much more efficient and comfortable system, okay? Take advantage of these as you can. All right, so terminology, we want to make sure everybody is speaking the same language. It's always interesting when we get phone calls and it takes maybe 5 minutes for us to all agree on the terms that we're going to call parts and pieces of our system. So pressure drop, that's the head loss or the resistance that our circulator has to overcome through the boiler, through the piping, through the valves, through the fittings, anything else that's out there. All right, so we need to know that. We gave you a easy, simple formula, but always be aware that this is, you know, this gets you into the ballpark. It's not an exact science. We have the potential here by using this formula to oversize by maybe 50%, but it'll get you in the ball game, especially when you're on a job that's already been installed and you're doing service work. So when we're looking at especially a one pump zone valve system, we want to measure the longest run. All right, if I got 3 zones, 4 zones, one of the zones will be the longest. I want to focus on that zone. You want to measure it out from the discharge side of the pump all the way through the house and back to the suction side. All right, you're going to have to do your best guesstimations once the piping disappears up into the basement ceiling. Okay, so get that number, multiply it by 1.5. We're adding 50%. That's what that means. So, because we can't see how many valves, T's, and what have you is in the system. Then we're going to multiply that number by 0.04 to make sure we're not going over 4 feet per second. And that will give us our head loss. So in this scenario here, it was a 150-foot loop. Now, if you recall, when we went over this, I told you guys to really focus in on 100-foot loop. 100-foot loop of copper, if you do the math, everybody should be saying to John via the questions, 6 feet ahead. Okay? So if you're not getting that, do the math right now. Take 100 times 1.5 times 0.04, and you should get 6. Why am I focusing on that? Because I can cut it in half. So a 50-foot loop is 3. I can cut that in half. A 25-foot loop is what? 1.5, right? And then you can start building from there. So now without even using a calculator, you should be able to type in what that 150-foot run is in head loss. Okay? So I'll give you a second. I want to see what you guys are coming up with. Any, John? 9. Perfect. 9. Okay? So again, that's the easy method, head loss. If you're designing a system from scratch and you've got copper charts and or PEX charts and CV ratings for valves and fittings and things of that nature, you can dial in your head loss perfectly. Another thing to think about when it comes to head loss is knowing if we're feeding air handlers. And we're getting more and more involved with hydronic coils for chiller systems where we're cooling and or heating. There's a pressure drop through that coil that we must take into account. Right? John just showed you when we were doing domestic hot water, figuring out the circulator, there's a pressure drop through that coil that has to be taken into account, plus the boiler. Okay? So besides the run going out to that air handler, we need to know what the pressure drop is across the coil. So I know the GPM, I know the length of the run, but I need to know the pressure drop through the coil. So in this scenario here, we're showing you a 4.7 water flow or GPM. The pressure drop brings you up to 4.5. If you took 4.5, then multiply it by 2.31, because 1 PSI is 2.31 feet of head, you will see that we are going to be just below 11 feet of head or pressure drop through that coil that we'd have to add to the pump so we know what the circulator, I should have said circulator, so we know what the circulator can overcome. Okay? When we figure out our circulator size, it's always based on, it's always based on GPM and head. You have to know those two numbers. If we don't know those two numbers, we are just flat out guessing. Once we know our GPM, we can plot it. So let's say for argument's sake, that coil was an 80,000 BTU coil and pressure drop through the coil was up to almost 11. We're going to be up here on this side. And I still have to include my length of run. But if I just stop there, I'm basically on that number 6 curve. That would be a 008. Okay? So it's GPM and head. That's how we figure out our circulators. You don't have that information. We're just guessing. Okay? And please don't be the guy to say, well, it's a 007. I'll just go up to the next size. No, because as you can see here on the charts, we have all different types of curves. We have long flat curves and then steep curves for different systems. Do I have a lot of resistance to overcome? Do I have to deliver a lot of GPM? Do I have to deliver a lot of GPM and overcome a lot of resistance? It's based on the scenario for the job. Yes, sir.
So we had a question, Jim, based on, you're talking circulators now, so I waited for you to get there. If you were to carry one SKU for a circulator on your service van, what would it be?
All right, if I'm doing residential service, Taco makes the 0015E3, gives you the low, medium, low, medium, and high settings. Yeah, we don't have that up here, but we're gonna, I don't want to let the cat out of the bag, but you think about this for your troubleshooting going forward. Gives you low, medium, high settings. At the medium setting, it is a 007E curve, so that means it can replace a standard 007. At the low setting, it'll hold 5 feet ahead all the way out to 12 GPM, 120,000 BTUs. Why am I bringing that up? Because if you walk onto a job and it's zoned with circulators in a residential home, you're probably going to be on the low side for a majority of those zones. And then if I have some high resistance, if I put it on high, this gets us up into that 16 feet of head range with some pretty good GPMs on the bottom. That would be a great pump to have. Now, it comes in 2 configurations. It comes with a 2-bolt and a 4-bolt configuration on the flange. So if I'm thinking more on the service side, probably the 4-bolt might be a good option for you. This way, when you get to the job, you have options in positioning that circulator when you're on the job. Okay. If I was doing a lot of new installs, 2-bolt flange would probably be something you go to. They're both the same price. It doesn't matter. But that circulator to me and to John and to all of us here at Wells Darby is a great, great service pump. Great service pump going forward. All right. Moving along. So we talked about the features of our ECM circulators. Sure start and the air auto blocking air purge. Okay. So these circulators, if they get stuck because it's a DC motor, right? I got a permanently magnetized rotor in there. And if there's enough magnetite in the system that could lock up the rotor, the circulator will rock itself. It'll actually vibrate and it'll try this up to 100 times to unblock that rotor and get flow going. So this is something that may happen. Your customer and you will never know it, and it keeps the system running, especially if it's been off all summer and now it's winter and it's time to go. And maybe somebody replaced the existing pump with this pump and never cleaned the system. So that's a great feature. If we get air trapped in the volute, all right, the system, the circulator will speed up to high speed and at 100 attempts to burp itself to get the air out. Again, something you wouldn't know, your homeowners wouldn't know, and it wouldn't affect performance of the system. Okay. On that flange itself, we give you the nut grabber feature, which saves you an additional hand. I put that nut in there, it's going to hold it in place, and then I can tighten it up out there on the job. And the bio barrier. Now, we're the only kids on the street that have this. If we've got that magnetite in the system, especially a cast iron system, and it's not if, we are going to have magnetite in there unless you have cleaned, flushed, and treated the system. That'll stop that from coming through and locking up the rotor. Okay, so even though Taco does make a mag dirt separator, we technically really don't need it with these circulators. Okay, my competitors are going to need it, but we don't have to. It's a great feature, plus the light. All right, for years, I'm in my 30th year at Wells Darby. Contractors would tell me, you know what the only problem is with your 007? I can't hear it. Now you got that orange light to show you that it's running. And this circulator is also going to change its speed based on a pressure differential from 0 GPM to 8.25. So as zone valves open and close, it'll change its speed. As it changes its speed, it's also changing the amount of amp draw it's using. It'll hold 10 feet of head, but it'll keep slowing down or speeding up to that 8.25. And then if we get past 8.25, we get onto the steeper side of the curve. And now we're running at full power, which is only 44 watts as it is. All right, we got to move. We got to get going. There's the sweet spot. 0015E3, same features and benefits, except it's a 3-speed variable speed pump, variable speed on low, variable speed on medium, and at high, we're at high speed and full power. All right. All right, VT2218, everything within that green band is where this circulator can operate. It's a delta T circulator, so it'll recreate pump curves as zones open and close. So we're not following one set pump curve, it actually recreates them as we're going along. I wish you could see what I'm seeing near me. Hurry up, Jim, I'm getting the hook. Let's go, let's go. All right. This is a pump I have on my system at home, and it's fantastic. It works great. Take advantage of it. So going forward, like I told you, we just added 0026E, 0034E. We have the ability on ECMs to replace all of our 00 series circulators. So the question of what pump I should have on my truck for service, the 0015E3 for flange, for both flanges is excellent, but you may have maybe one or two of our ECMs on there, and that'll help you on any job you walk in on, even like commercial. All right, we talked about system curves. So when we pick our circulator based on GPM and head, we have to make sure that we are going to be either on or below the pump curve that we're going to choose. And then what will happen as zones open and close, physics says it has to follow the pump curve. So even though in this scenario, this is where I want to be based on GPM and head, I'll end up performing up here on the curve. And as my zones open and close, the circulator will ride back and forth on that curve. So this is why we never really want to oversize circulators, because as I go further and further to the left, you can see the head that it can overcome is greater. We start to shrink our delta T, okay? Take advantage of the universal hydronics formula, take advantage of that head loss formula, make sure you're sizing your circs right. Okay, so the moment we've been waiting for, this is our favorite part, troubleshooting, okay? Troubleshooting, root cause troubleshooting. Look at this scenario here. Here's the scenario. We're giving you GPM per zone. We're giving you pipe size. We're giving you a boiler size. But here's your problem. Everything works. You show up on the job and their building owner or the homeowner is telling you it's not heating well. So I'll give you a minute. Let's take it one step at a time. Is that boiler the right size? And I'm not going to tell you how to figure it out. Let's see what you're thinking. A little bit of math involved. Let's see what you're thinking. All right, Eric, I think we're going to move along. All right, I guess I've been a little long-winded. All right, so if you look at this, the problem was not enough heat. Are we over pumping? Are we short cycling this boiler, or is the boiler not sized correctly? Well, if I look at the GPM that we gave you per zone, if you add that all up, I believe that's about 17.5 GPM. Remember, you can take your universal hydronics formula and do it backwards. I can multiply the GPM by 10,000. That would mean it's 175,000 BTU that we're trying to move if all circulators are running. My boiler is only 140,000. So is it over pumping or an undersized boiler? Okay. If it's over pumping, if it was undersized boiler and I need to move 175, is that supply header and that boiler piping right? I need to move 17.5 GPM. Can you move that through 1-inch pipe? Look at your charts. Can we do that? I don't think so. So the piping would have to be changed. All right.
Jim, the chatter coming across right now is fantastic. It's awesome. So it's everything from boiler too small to pipe too small to, on and on it goes. It's great.
Great. The whole idea of the root cause troubleshooting is so you're using all the information that we've given you and you're looking at the system probably differently than you ever have before. So if we're already talking about that, this is great. You guys have done a great job. All right, let's look ahead now. So here's this job where we've got a cast iron and priority domestic hot water. The boiler's 80,000 BTUs. So you can either write this down and maybe draw it out at the same time. Got 80,000 BTU boiler. I need a DHW of 80,000 BTUs. I got 4 zones at 2 GPM each. I got a pressure drop through the boiler 3 feet ahead, 6 feet ahead for the domestic coil. My system side has got 6 feet ahead. I need you guys to tell us boiler or system circulator, size circulator, domestic size circulator. Give me the piping size for the boiler, all right? Give me your zone pipe size, domestic hot water pipe size. So if you're thinking about how to draw this out, I'll give you a little glimpse here. So maybe sketch it out. Sketch it out like this. That helps me. I'm a visual guy. So give you a second to quickly sketch that out.
So while they're sketching, Jim, just to fill a little time here, got a question. What is the proper term for moose antlers?
Yeah, moose antlers.
I'm not sure if this is a joke. I'm waiting for the answer from him or what. But yeah, moose antlers.
Yeah, moose antlers. Actually, years ago, I'm out at Worsbo at the time before it was called Upanor, and the instructor Johnny B was drawing this up there, and I'm out there with guys from New Jersey, guys from Long Island, and guys from Long Island. They're a riot. Any New York guys have got wicked senses of humor. He's drawing it up, and the guy yells out from the back, "Moose antlers!" And that's what it's been called ever since. So it's moose antlers. So if you've got this drawn out, let's go back. All right. So what is the pipe size? So we want to start with pipe size? Yeah, let's start with pipe size. Let's work backwards.
1 inch,
Right.
1 inch boiler, 3/4
Right.
zones, 1 inch domestic.
Great. So what we didn't tell you, and we do this on purpose when we do it with people in front of us, we didn't give you a delta T. So we'll use a 20-degree delta just to keep things moving along here. So if you're picking 1 inch, you're right, because it's 8 GPM, and we can handle that. If you wanted to even bump it up to 1.25 inches, that's not a bad deal. Okay. Now, what was our circulator size for the boiler?
I'm still waiting for circulator size.
Okay. You know what your GPM is. We're giving you the head. Ooh, the silence is deafening. I hope you think this is fun, because this to me is a lot of fun.
I got crickets.
Crickets.
Crickets. Yeah, I just got one in.
They're thinking.
Yeah, they're thinking. They're calculating.
I hear clicking.
I see smoke. Got 1008.
1008. Okay.
What page is pump size on?
Well, in your
Take-O book.
take-O handout, I believe that would be page 52. But I'll give you a little clue. Don't forget your ECMs.
Yeah. 52. And it wouldn't hurt to look at 48.
Well, how about if you guys give us the GPM and head?
Oh,
What happened?
nothing. Keep
Nothing.
going.
All right. Well, what's the GPM? It's got to be 8 GPM. My system is 6 feet ahead, but I do have a 3-foot drop through the boiler. So we're going to call it 8 at 9. Okay. What would you do at 8 at 9, guys? One option could be the 007E, because at 8 at 9, a little tough to see for me here. I believe that's around the 8-foot mark. 9 feet ahead gets me right there. So that would be perfect on a 007E.
I got 007 just kicked in here.
Yep, that'd be perfect for
007E.
a 0015E3 at medium. All right, that would work out really well. What about the domestic side, guys? Right? Basically the same scenario, right? 6 feet ahead, 3 through the boiler, right? Those same size circulators would work. Okay. And I think we exhausted this one here. We got our pipe sizes and the zone pipe sizes, right? Each one was 2 GPM. What do you guys think for zone piping? John is typing furiously. I wish you guys could hear it.
And laughing furiously.
Probably you all would go with 3/4 pipe and at 2
we got
GPM,
3/4.
that would be fine, right?
Yeah, 3/4.
Could we bring it down to 1/2 inch? Yeah, but you're probably going to use 3/4 anyway. All right, moving forward. Any questions on that? Anybody lost in the dust here, not following along?
No, just tons of funny answers and we're cranking along.
Funny answer. Is my zipper down? What's going on? All right, moving forward here. Condensing boiler, priority domestic, primary, secondary piping, a little bit more of a challenge. And this one I'm going to leave open because John alluded to this when we started today. There's your boiler BTU, there's your domestic BTU, there's your GPM. We're giving you the head losses. We're looking for the same information. Here's a sketch of it if you want to quickly draw it out to help you out. Okay. It should look familiar to you, something we showed you earlier. Okay. So the question is, right? Well, what's my boiler circulator size? What's my system circulator size? What's my domestic circulator size? We're staying within the 20-degree delta, but what's going to be interesting is what you guys decide. I'll leave it at that. No more music, that's okay. I think we wore that out. So John, what are guys coming up with? How are they sizing the boiler?
So I didn't get a boiler size here yet, but I got 10 GPM at the boiler, 8 GPM for the system, 15 GPM for the DHW, which they're correct on all of those. But just fire back a boiler size to drive that system.
That's correct. You guys, hope everybody heard them. You know what size boiler you're going with, because that really is going to end up dictating everything else.
We got a 100,000 BTU boiler just came in.
All right, so that gentleman went for 100,000. He's going to follow the scenario of, you know what? Storage is less money in BTUs, as John said earlier today. All right. If you went to 150,000, you could be really dramatically oversizing that boiler, which isn't going to help the system. So now if he's gone to 100,000, that's 10 GPM at the boiler. All right. So now that'll tell you what your pipe size is going to be. That's going to tell you what your circulator size is going to be. All right. Same thing for the domestic side, pipe size and pump.
So we got a 0012 for the circulator. We got 1.25 inch header piping, 3/4 zone piping, 1 inch DHW piping.
So what does he have for the boiler piping?
1 1/4.
So we're using 10 GPM, 1 1/4? Yep.
He's right on the edge.
He's right on the edge. Well, 10 GPM.
We're teetering.
1 1/4 will be fine.
Yep.
It's still 10 GPM for the domestic. That's got to be 1 1/4. All right. So now what's our circulator size? I got 12. I'm sorry. Circulator's 12 feet ahead. All right. 10 GPM. What did you guys come up with?
You got 0012.
All right. So I did put this chart up there. So let's take a quick look. 10 GPM, 8 feet ahead. Hard for me to see, but we're going to be in that area there. And that's the number 10 curve. We're going to be up in there. That's your 0012 right here. All right. So that looks like that's a good choice. Okay. Still 10 GPM for the domestic, correct, guys? Yep. Everybody say yes.
It did.
So now I got 6 feet ahead there, but I got to pull through the boiler too. So what's the head going to be? What do we get, John? Guys are thinking 18?
Yep.
All right, cool.
You got somebody's phone number? What else here?
And I don't think they're asking you for a date. Call me. I'm confused. So if I need 10 G, we're having fun.
Yes,
10 GPM up at 18 feet ahead. We're out here in this land. All right. So that's the number 12. All right. You're talking 0014. That's hard for me to see. I apologize.
I got 14. Yep.
Yep. 14.
Yep.
10 GPM at 18. We could also be in that 14. You could also be at 0011 in that range there. All right. I believe everybody is getting this.
Yeah.
All right.
Yep.
At 2 GPM per zone, everybody's going to be using 3/4 pipe. I think we can move on from there. All right. Okay. Here's something else that we like to throw at you. When do you use circulators or zone valves? All right. We can cross the river and there will be a majority of the Long Island guys that like to zone with circulators. We get redundancy. If I lose a circulator, I don't lose the whole system. That's great. And we come over here, it's kind of more of a 50-50 or maybe even a little bit more on the zone valve side. But one of the things we think about is if it's a large system, all right, larger than 130,000 BTUs, having a circulator could cause us a problem if we have a small zone calling, all right? And if it's just a single speed circulator, we're going to be over pumping dramatically, and we could short cycle that zone in the boiler. So we feel that if you're at 130,000 BTUs or less, all right, that's a single circulator zone valves. If I'm at that 130,000 BTU and higher, that would be a circulator job. And let's give you an example here. So here I'm showing you an 85,000 BTU system, 3 zones. And the first zone is 81 feet, the next one's 112, and the next one's 137. So if I was going to do a circulator at a 20-degree delta, that's 8.5 GPM. And I really have to just zone in on that 137-foot loop. If you do your math, and I did the math over here for me already, I think I did. Or no, I didn't. But 137, that's going to get us probably in that 7 and change feet of head, I believe. All right, if somebody does the math, let us know, okay? And again, that's going to bring you to that 007 type of range. That's going to bring you to that 0015E3 type of range and what have you.
8.22.
8.22? Okay, 8.22, very good.
So good question came up. What about a monoflow system?
Monoflow system. Well,
Different animal.
they're different animal. They're generally pretty big GPM, but it's going to depend on how many convectors and or zones of radiation you got to come off it. And do I have a monoflow T in front of that or 2? All right. If I've got 1, all right, there's less head involved. If I got 2, there's even more head involved. And we do have to know how many of those monoflow Ts you've got there.
Brand, material built out of,
Yep.
and how many?
Did everybody hear that? We need to know the brand, the material, and how many. Because they have the potential, I think a 3/4 can have the potential of an equivalent length of pipe of like 70 feet. That's substantial, guys. That's substantial. So that could tell you that maybe that 007 is not the right one, all right? But it's not also as big as you think, but we need to know. Okay. That 175,000 BTU system, just doing some simple math, we divide that by 5, we're talking about 35 BTUs per zone. All right, so now if I was going to do a circulator per zone, that 62-foot length run, that's only 3.72 feet of head. All right, yeah, I did the math before. The 89-foot run is only 5.34 feet ahead. The 100-foot run of 102, everybody should know that's 6. It's going to be a little over 6. We're going to call it 6. 122, well, that's going to get you to 7.32, and the 151, everybody should run to that as 9. So I could look at my 00 chart. I can look at my 00 chart and go through all of that, 3.5 GPM and those different head losses. I could do it that way and pick different size circulators. I could also go to that 0015E3. And if I go to the first one, we're 3.5 at 7.2, 3.5 at 7.2 down here. All right. I'm sorry, 3.5. I'm sorry, 3.5 at 3.7. That'll get me on the low side. That's good. The next one, 3.5 at 5 and a change. Again, that gets me on the low side. 3.5 at the 6.12. Well, by math, I should say medium, but I could live dangerously and put it on low. All right. And the 122, that's going to get me to medium because we're at 7 and change. And the 151 is going to get me at 9. I could put it at medium. So I can have one circulator, right, and just change the speed based on zone size, okay? This is the advantage of having the variable speed circulators. And I just want to address one thing. You're going to see that green mode line there. Since they're not going to vary their speed per zone, they will end up at a constant speed, and they'll end up on that green zone line, right? It's on the chart. Green mode is on there. All right. Static pressure, we got a problem here, all right? We got a problem here. Here's the 100,000 BTU boiler. Here's my VT2218. Here's my pipe size. There's your total equivalent length of 145 feet. There's the system working pressure, all right? Is everything right here? You guys got to tell me. So while they're doing that, let's discuss that green line. Did they
Green
take
line.
that out?
No, green line is, so ECM circulators have to hit a certain efficiency. And originally, when they launched the 007s, it was if it had a demand for more than 24 hours, it had to adhere to a specific energy level. So it would go to, it wouldn't be orange anymore, it would turn green, and it would run that green line curve
Okay.
to reduce the power.
Reduce the power.
This mostly happened in Massachusetts. We didn't see it here. They've extended that time period out now further. So if you have a green light and you are not heating the zone properly, power it down. You need to break the heat demand. And then you can put the heat demand back on. It'll go back to its orange operation, running its normal curve.
My bad, I misspoke. So since if we zone with the circulators like I just went over with you, and we're getting intermittent calls like that, that wouldn't happen. If it was a 24-hour call, that's what's going to happen. My bad on that.
Run that green curve.
Yep, my bad.
And they may have insufficient heat once you start running the green curve.
Yeah, so if we're running into something like that, we got another problem going on.
Yeah.
All right, so what do we got here on the static pressure size here, guys?
Pressure should be 21.6.
How'd they come up with that? Did they take 41 times 0.43 and add 4? Absolutely right. Is the pipe size correct? We didn't give you delta T, but let's stay within 20. Everybody agreeing on that? Okay.
Good.
And would the VT 2218 handle this?
Also looking good.
Yes, it would. Excellent. Excellent. Let's take a look at this job. I know we've gone over, but we're just having way too much fun. So stick with us here. All right. So here we're showing you primary, secondary. I'm giving you the BTUs of the boiler. I'm giving you the head loss of the boiler. So is the boiler pipe size correct? Is the circulator size correct? Let's take that first. So tell me if what's going on there. What do you think? First, determine your GPM. Now you got your GPM ahead. Look at your pump charts. Pick the proper circulator. And once you know your GPM, pick your pipe size. How are we looking?
Pretty quiet over here.
Oh, no. What happened? Well, if we're looking at the BTU of the boiler, and that's our net, 20-degree delta, you all should have got 9 GPM. 9 GPM, what pipe size should that be? If you said 1 inch, I'd take it. If you said 1.25 inches, I'd be even happier. Okay, so what's 9 GPM at 15 feet ahead? Look at your pump charts. Look at your 001. 9 at 15, where's that taking us, guys?
Circulator is undersized.
Circulator is undersized. That's like a 0014 at 9 at 15. We're in between, all right? That's a 0014. So look at the system side. The system side, I guess we're going to stay with the same BTU, or are we going to adjust the delta here, John? What do you want to do?
Give me 20.
All right, so same 20-degree delta. Okay, so it's 9 GPM. Your longest loop is 102 feet. There should be no math involved there, guys. You know where that's going to be. So 9 at 6, where are we going to be? Okay. 007 will work. 007E will work. 0015E3 at medium will work. Okay, good. All right, so this is my favorite one. This is my favorite one. Take a good look at this. There's your boiler BTU. There's your indirect BTU. All right, boiler and header piping is 1 1/4 inches. There's your heating load for space heating. And we're telling you got 5 zone valves. We're using Honeywell. We're using Honeywell only because that they just own that market. All right, so we're not picking on them. There's a zone valve going to the domestic hot water. All right, you got 3 zones of heat, space heating at 2.5 GPM. And then you got one zone of heating at 4 GPM. And your domestic piping is 1 inch. The system runs. You got to call because domestic hot water is not consistent. They're running out of hot water. And little Sally's room, that's the room that gets 4 GPM, works okay, but when it gets really cold out, it's not keeping up. And this everything on here is running properly. What do you think? What do you think, and how would you fix it? You don't want me to do that, right? How we looking? Guys answering?
Is it in priority is the question.
Yeah, let's assume it's prioritized, but
Okay, it's prioritized.
that's fine.
Hey, troubleshooting guys, remember, always do what you know first.
Good point.
Always do what you know first.
I'm being sneaky here. You know, we threw zone valves up there. So unless you really know flow rate through zone valves, I'm really leading you down the path here. Unless you really know flow rate through zone valves, you may be confused.
I got on here change zone valve, and that's a good answer, but which zone valve am I changing?
Right.
What was the name of the room?
Little Sally's room.
Oh, Little Sally's room. Okay.
So today it's going to be 50 degrees. Little Sally is going to be happy while she's doing school at home.
Hey now.
Hey now. But last week when it was 20 degrees out during the day, little Sally needed a sweater. She wasn't happy.
Oh, excellent here. Little Sally only has 35,000 BTU going to her room.
Fantastic.
And the domestic hot water tank only has 35,000 BTU going to it.
Fantastic.
So Sally in her room is not happy, and Sally in the shower is not happy. Poor Sally.
Poor Sally. But our job is to make Sally and all of our customers comfortable, and whoever put that answer in is absolutely dead nuts on. That gentleman knows that a standard Honeywell is only a 3.5 CV through the valve. That's 35,000 BTUs. You're 5,000 BTUs short. So what do? I could change the zone valve. Shameless plug. Take a Zone Century. It's a 10.3. And if you're using the press version, it's a 9.5 CV. So that would fix little Sally's room. What about the domestic? Yeah, we got to take it out. So some guys usually say, well, I'll put a full port 1 inch Honeywell in there. So if you know the CV of that, guys, that's only 8. So now we're talking 80,000 BTUs. You got to move 130 because your boiler size is 130. I got to move 13 GPM through there. What should we do? Because Miss Little Sally's mom is not happy now, so that's a big one.
Make it a circulator.
Absolutely right.
Make it a circulator to domestic.
Absolutely right. And here's what we would tell you to do. Add a circulator and take it off right here, right? John calls that direct hot water. Pull it off right here. Prioritize it. This way we only drive one circulator. We don't need to drive this circulator, and we can fix that domestic hot water problem.
Yeah, Mark also said it wouldn't be a bad idea to increase it to 1.25 inch pipe, which is also a good idea.
Yep, absolutely. Absolutely. I hope you guys all got that. This is something that we see pretty often. All right, you'd be surprised. So I just put up this chart to help you guys help size circulators, but you guys got the gist of what that one is. So we've gone a little bit over, but not much. And I really feel you guys did a great job, because the whole idea of this training is we don't want you to do things like this. All right. And that's no joke. That's a job we've actually seen. All right. Don't be this guy. Don't do this. Do the math. We pounded the fundamentals for 4 classes with you. If we pound the fundamentals and we do the fundamentals, our troubleshooting should be much simpler, because we don't have to worry about all those other things being, are they correct or not? Pound the fundamentals on all your jobs and you can't go wrong. So you don't want to do things like this. God, you don't want to do things like that. the thing that kills me is that guy stepped back when he was done and said, look what I did. And he was proud of it. All right, it's a mess. All right, so we thank you very much. We have a blast doing this job. What are we doing? We're pointing. Oh, look at the cam. I'm sorry. I'm getting used to this. This is new. All right, so thank you very much. You have our contact information. Email us, call us, all right, at any time. I've been having some conversations with guys as the 4 weeks has been going on via email, asking questions. I've been answering them. Same thing with John. So please, anytime, give us a call. They're making fun of me.
So yeah, we really want to thank everyone. We know this is a big donation of your time, and hopefully you're leaving here empowered with the information to go out there and solve a hydronic problem. Usually when we do this class live, there's always at least one student within the room that comes back to us and says, now I understand why it takes 30 minutes to produce hot water at my home, because I have a 3/4 zone valve, whatever it may be. We wanted to empower you guys to be able to go out and just be confident in what you're seeing, finding the root cause of the problem, and coming up with the proper fix. Because the attendance was so overwhelming, we're actually going to have another 4-week training class. It'll be on Tuesdays, starting the 9th of March. It'll be the 9th, the 16th, the 23rd, and the 30th of March. It will be again at 7 a.m. Jim and I will probably tag team it again. And if you go to our HVACinsiders with an S.com website, we have a podcast there. We put majority of these trainings on that site. And you can also see our future training. We are booked out every Wednesday morning, starting next Wednesday through the 30th of March, with all different types of training. It will be, we're going to try to do as much as we can as we did this class live. We've learned a ton. We appreciate everybody sticking with us. We are getting a ton of communication, a ton of involvement. It's greatly appreciated. We look forward to seeing you guys at one of our next training classes. So for Jim, myself, Eric, Chris, thank you very much. Vince Menino, our IT guy, was a big help here getting this launched. And we just appreciate everybody's help and participation.
What's our next class other than the next 4-weeker?
You are up.
That's right.
To teach people how to sell.
Next week, selling comfort systems. If you want to have some ideas on how to grow your business, if you're having problems making profit margins, give us a look-see on that one. I expect a lot of interaction with that and a lot of pushback. Hope to see you next week. Thank you again. Have a great day.